Hi everyone and welcome back to this YouTube series on well-modeled LES. So this is going to be the last video of the theoretical part of the course, and today we're going to look at the different errors which occur in well modeling. We're going to sort of dissect them and look at them individually in detail. And then we're going to finalize the video by looking at the last step in the whole wall modeling algorithm, and that is how you enforce the wall shear stress in your LES simulation. So there are several sources for errors in wall modeling, and in the previous episodes we sort of mentioned pretty much all of them, I think, but here I really want to concentrate on each of them in a bit more detail so that we get the global picture just summarized in one particular video. And the first error we're going to talk about it's on the slide now is basically the errors in the sampled quantities. So as you remember, any type of wall model you use basically relies on sampling some values from the LES solution, right? So typically it's velocity, can also be velocity and pressure, or velocity and pressure gradient, whatever, it doesn't matter. But the point is you have to sample something and that goes in as input into the wall model. And the thing is, if these are significantly erroneous, then you're not going to get a good output from your wall model. So basically, it's just garbage in, garbage out principle, right? So if what you put in is bad, you're not going to get a good estimate of tau wall from your wall model. And of course, whether these are accurate or not depends on a lot of factors. And most importantly, they don't really depend on the wall model itself, right? It depends on the other parameters of your LES. So in particular, the numerics you're using, SGS modeling, your mesh, etc., etc., etc. So all of those are very important, because if you don't provide the correct settings in the simulation, the wall model is not going to save you from that. That's probably the most important thing I want to say here. But there's also one parameter of the wall model that is actually coupled to this error, and that is the distance to the sampling point. So what we call h, right? So this is basically the distance from the wall where you're going to sample these quantities. And it has been shown quite a while ago now in this paper in Physics of Fluids by Kawai and Larson that choosing the wall adjacent cell is suboptimal in terms of the sampling point. So you should never sample from the wall adjacent cell. It's easy to show why. I'm not going to do it here. You could just read it in the paper. But basically, it's reasoning about the size of the turbulence eddies that you have to resolve, and the grid resolution, and how it all connects into the fact that if you always sample from the wall adjacent cell, you're not going to get a good result. And basically, it will result in a poor prediction of tau wall due to the inaccuracy in the velocity signal. This is something from a paper where I'm a co-author of this figure. So it's Reza Ravesh from Computers and Fluids 2019. And what we see here is the error in the friction velocity. And on the x-axis we have the sampling height, so h, and we divide it by the boundary layer thickness here, or the channel half height. This is from channel flow simulations. And there are a bunch of different curves corresponding to different simulation parameters. There's like different SGS models and different grid resolutions, etc., etc. But that's not particularly important for us. What we want to see here is that basically the error in u tau is pretty much constant. It sort of levels out, at least for all the whatever you use. It sort of starts leveling out as you go away from the wall. Things are a little bit shaky for the blue curves because it uses the linear scheme, but there's no reason to go into details here. But what we want to see is that the worst error is that always when you sample from the wall adjacent cell, which is just the closest point to the h over delta 0 on the graph. So as you can see for these red lines, basically the error is just off the chart here. It's somewhere below there, so it's really under prediction. And for some of the curves, we can see it's like, for example, 8% here, and it's also a bit wiggly for some of them. But basically, it's almost always the worst if you use the wall adjacent cell. So across very different simulation parameters. So usually the second cell is a safe bet. We're gonna talk about this a bit more when we get into the practical part of the course. What should you actually choose? But I can say already now, but typically the second cell is already a pretty safe choice. Maybe an even safer choice is the third cell. Okay, so that's error number one. And I would say like this, basically if your wall model is decent in terms of how it correlates with the physical flow situation, so if it can support the flow conditions that occur in the flow, then this error is usually dominant, I would say. So it's really important to keep these considerations in mind. And the second error is exactly the inaccuracy of the wall model itself with respect to the flow conditions. So that can also be off, right? And basically this is what we've been discussing most of the videos, right? How do we make a wall model that can account for different types of flow situations, such as with strong pressure gradients or whatever, roughness, you name it, all the different things you can encounter. And this is an error which is then completely intrinsic to the wall modeling itself. It has nothing to do with the outside LES in contrast to error one. And well, as we already know, so usually the wall models are very accurate if you have a smooth wall and no pressure gradient, right? So then these equilibrium models work very well. If this is not the case, then potentially this error can be large, depending on the wall model. And this is where all the discussion comes into, should we use maybe a PD wall model to account for the non-equilibrium effects, or do we disregard that and say, okay, we're going to use a simple law of the wall anyway? So this is the error number two. And the third error is sort of more subtle. And we've discussed this already as well. So that's the error which is due to the fact that you're sampling a transient signal, which is the filtered velocity, right? But what you're using is a Rance model, where basically what we are interested in is the average velocity. So we're giving transient input to a Rance model, and that results in some kind of errors. So we've discussed that when it comes to PD wall stress models, that you get these resolved stresses, turbulent stresses in the Rance model, which leads to problems. But whatever model you take, this manifests itself in some kind of way. So one way to get rid of this, right, is to just average U before we input it into the wall model. So that's just a straightforward strategy that has been used by some. But what we have to keep in mind is that if we do that, then the output of the wall model becomes the averaged wall shear stress, right? So not the instantaneous. So we got rid of the problem that, the input signal doesn't correspond to what our wall model is, but on the other hand, our wall model doesn't exactly spit out the quantity we want it to spit out. Instead, it spits out the average quantity. So we still have an issue in principle. But some people say that, okay, this is actually fine. We can just apply the average stress as a boundary condition, and this is okay. So for example, you can look at this paper, also Physics of Fluid by Lee and colleagues, 2014. They do exactly this. They consider channel flow and a turbulent boundary layer on a flat surface. And they just apply the average wall shear stress, and they show, okay, look, we get pretty decent results, at least for the quantities we are considering here. So that's one approach, right? So you just kill the transient signal, both in the input and in the output of the wall model. The other alternative is we say, look, okay, we are going to feed a transient signal into a Rance model. Yes, that's true. But we can hope that maybe the transient output that we get is not going to be completely unreasonable. Sorry, there's a typo here. It should be tau wall here, of course. So we use a transient U, and we want to predict the transient tau wall. Okay, so the question is that, I mean, you can always hope, right? But is it reasonable to hope for that? And it turns out that maybe not so much. So what we did, this is a picture from a study that we've done. And what we have here again is h over delta on the x-axis. And what we have here is the correlation between the correct filtered u-tau signal and the one which is predicted by the wall model when we feed it the transient signal sampled at this particular height. Okay, so let me just say that one more time. So let's say we take this data point. So this means that we're going to grab a velocity signal from this height, and then we're going to put it into the wall model. In this case, I think it's just the Spalding's law of the wall. And we're going to get some u-tau values, right? And we have the full velocity signal saved. So this is like an a priori study. So we have the velocity signal saved. And from this velocity signal, we're going to get this u-tau star signal from our wall model. But we also actually have the correct u-tau, the real u-tau, also saved. Okay, so we know what the real values are. And what we're looking at is, okay, are the values we are predicting from the wall model correlated to the correct signal? And as you can see, well, obviously, the further you go from the wall, the less the correlation. That's sort of expected, because obviously the velocity values further from the wall are less and less correlated to the values of the wall shear stress. So this is expected. But the reasonable question is, so how well are they correlated within the region where we can sort of think of putting our sampling point in, which is probably up to about h over delta 0.3 or something. And what we can see is that the only good correlation is in the first off-wall cell, which is here. And then we get about 0.6. So actually then maybe we can hope, right, that we're actually getting something reasonable by applying this procedure. But as we said before, when we discussed error source number 1, this is actually a suboptimal point due to different reasons, right? So there's a clash. On the other hand, we seem to want to use the near wall cell if we aim at predicting the transient filtered tau wall signal. But on the other hand, we said, look, this is going to cost us because the accuracy of the U is actually not that good. So we're going to get the error in the mean instead. And typically the first consideration prevails, right? You want to at least get the correct mean tau wall. The fluctuations are, after all, maybe secondary. So yeah, it's a bit of an issue, but I think it's still a bit open. I mean, like 0.3, is that justifiable? Like, is that good enough? I mean, you still have some correlation. It's not zero, at least. And you can use the second off-wall cell for sampling. So is it worth it or not? I don't know. I would say like this, that I think it's still the standard procedure is not to apply any time averaging. So the standard procedure is just to eat up the fact that this is not equal and we use this anyway. This is what most people do still, I think. But the time averaging idea seems to gain momentum in the literature, I would say. There's been several papers recently that, in the last couple of years, that advocate for time averaging the input for one reason or another. So this is where we are now. Now there is, of course, another option, and the other option is to actually try to build some separate model for the fluctuations. So we're going to use our RANS model with a time averaged input, and that is going to give us a good prediction of the mean quantity. But we also want to employ some kind of separate model, which is going to model the fluctuations around the mean, which is not going to be a RANS model, obviously. And the question is, what is that model? And I don't know. But that's sort of an approach which is reasonable to pursue and try to develop such a model. There are, as far as I know, there's only one attempt in the literature to do that based on the so-called IOC model. And the IOC stands for inner-outer scale interaction, and has to do with the interaction between the turbulent scales in the outer and inner layers, which goes back to this paper by Marusic in Science, which I believe I referenced in one of the earlier videos when we discussed turbulent boundary layer theory. So this is still I think this is something which can be developed in the future, but as of right now, basically nobody does this. But we'll see. Okay, so this has been all for the error sources, and now it remains only one thing for us, and that is the final step of coupling between the LES and the wall model. So we already covered two steps, right? The first one is the input to the wall model, and that is that we basically just grab data from the LES solution at some height h into the wall model. And then the wall model gives us tau wall. That's the second step, and this is what we've dedicated a bunch of videos now, right? So now we know how the wall model works and how it predicts tau wall. So what remains is the first step. We want to insert that tau wall back into the LES. Okay, so this is here step one. So we got tau wall from the wall model. What is next? So let's just write out again what tau wall is. So here I write it component wise. So this is this quantity, right? So it's viscosity times the wall normal gradient of a wall parallel component evaluated at the wall. So when we look at this expression, so this is going to be given from the wall model, right? So if we want to set this right, we can either play with the viscosity value at the wall, or we can play with the wall normal velocity gradient. So we can change either of them in order to satisfy the correct value of tau wall, which we're given from the wall model. And the absolute majority of the works, they deal with the pressure gradient. The velocity gradient, right? So what we do is, okay, the wall normal component is irrelevant. We just set it to 0, right? So it's this non-penetration condition. So a wall normal component is 0. And for the wall parallel components, we just apply a Neumann condition, right? That's what setting the gradient is. That's just a Neumann condition. So this is basically it, right? So you treat the different components of velocity a little bit differently. Now, here I've wrote it out for the components, right? So, but sometimes the wall model will just give us the magnitude, right? For example, if we use a law of the wall, it's not going to give us the components of the shear stress, it's just going to give us its magnitude. And that's okay. If we have that, we just scale the components proportionally to the UI, to the components of the velocity in the near wall cell. So basically, if you have like the velocity in x is 5 times larger than in z, let's say, then the same will hold for your shear stress vector. So that's what seems, usually I also have to say that usually this step is not really talked about that much in the literature. It just sort of assume that you know what they're doing. But as far as I can tell, almost always they play with the velocity gradient. In contrast to this, and relevant for the discussion here also, is that in open foam they do something different, and that is then change the nu, right? So that's the other alternative. And the way they do that is they say, okay, we're going to use some additional viscosity, which we can call nu t, and this fits well into the open foam framework because usually you have this nu t field anyway, and physically it's 0 at the wall. Usually it corresponds to the subgrid stress, to the subgrid viscosity. So at the wall that is physically 0, right? So we have like this field that we can toy around with like a dummy field. So the idea here is that we're going to add an appropriate amount of nu t such that we get, after we evaluate this expression, we get the correct value of tau wall, which is given from the wall model. And of course, if we look at that, we can easily see what kind of nu t we need to plug in. Well, we simply divide by this, right? The velocity gradient that we currently have. And this is also known from the wall model, and we subtract the molecular viscosity. That's about it. So, yeah. So that's the alternative approach, and the good thing about that is that then we can just use no slip for the velocity, right? We don't need to look at the different components, yada yada yada. We just set no slip, and that's it, just like we do in a ordinary LES, and that's quite convenient, right? So I think that's quite nice, and it makes the simulation quite easy to set up. I don't think. As of right now, I don't see any reason why one of these would be superior to each other. to the other, sorry, because they both achieve, in the end of the day, they both achieve the same thing. It's that you get the correct contribution from the wall when you evaluate the stress, right? So it seems, at least at face value, that they're completely equivalent. That being said, I want to try and implement this one in OpenFOAM. I've done some initial attempts, but I haven't quite finished sort of that study. I think it's still worth a look, and looking at this for this step of the whole algorithm maybe a little bit closer. Yeah, that's just my intuition. But this is what is done anyways. And I think we are done with the theoretical part of the course. So the continuation is going to follow in 2021, obviously. I don't know how many videos it's going to be, probably something like 4, I guess. We're going to, well, the last videos are clear. We're going to look at my library in OpenFOAM. We're going to look at how we're going to install it. We're going to look at how we set up the case. Look at what's available, etc., etc. But there are some stuff I want to cover before that, and that's just basically looking at some of the more practical aspects and looking maybe a little bit into the studies that have been done, so that you get some sort of practical intuition, for example, for how a wall-modeled LES mesh looks, how dense it is, how many, just a sort of a feeling, how many millions would I need to simulate, for example, such a flow, etc. So you can evaluate also the computational complexity. So these are the ideas. But anyway, as for now, I wish you a very Merry Christmas and a Happy New Year, and stay tuned for the next videos. See you guys.